Hello viewers, welcome to Big Boy Physics. In today's video, I have brought you a problem from the topic of mechanics, and it is from the source, that is Jaan kalda handouts mechanics. This is question number 65. You can see that it's tagged with orange color, which indicates that this is a rather difficult problem. And another thing to assume that this length in the problem, as shown in the figure, is actually equal. That is, the linear dimensions of the rods are same. Let us read the question. Three little cylinders are connected with weightless rods where there is a hinge near the middle cylinder so that the angle between the rod can change. So at the middle cylinder there is a hinge which connects both the rods so that the angle between them can be changed. Now the two cylinders have mass m and other has mass 4m. Okay, so you can see that the right side cylinder has the mass of 4m. You have to find the acceleration of the heavier cylinder, that is the cylinder with the mass 4m, because it's the heaviest. So it's also saying to ignore the frictions and assume that this apparatus, whole apparatus, is in the vertical plane. Okay, now how J would ask you the problem, maybe they may ask in the integer type format. They'll say you that the acceleration is given as g by n, so you have to find n. Okay, pause the video, give it a try for 3 to 4 minutes, then we are discussing the solution. Okay, so let's get started. So I have taken this figure in a new page, the same figure. Now let us assume that the acceleration of A, it should be horizontal by the constraint due to floor. So let the acceleration of A be A I cap, that is pointing towards the right hand side direction. Now observe that B will be rotating about this AB rod, right? So you can say that acceleration of B with respect to A will be only tangential in direction. It cannot have radial acceleration because the rod will else compress, or it cannot have the term omega square r in the acceleration because initial omega is also 0. So the only acceleration which is left in our stock is the AT, that is angle tangential acceleration, which is equals to alpha r, where r is the length of the rod. Okay, let us denote it as a1. So suppose this b has acceleration perpendicular to the rod, that is a1. So the total acceleration of b will be acceleration of b with respect to a plus acceleration of a, which I have denoted with the red color. So just add another a vector that is parallel to the floor surface. Now similarly we'll be doing the same analysis, that acceleration of C with respect to B is again in the perpendicular direction. So marking with a yellow color the acceleration of C with respect to B as A2, and the sum of accelerations now A1 and A respectively. Now by the floor constant, you know that this mass m will be lying on the floor only, it cannot get up easily. So I can say that a1 plus a2 by root 2 is equals to 0, first relation. So I can say a1 plus a2 is equals to 0. This is first equation. Now observe that fx is equals to 0. The net force on the whole apparatus is 0. This implies that summation of ax into m is equals to 0. Hence, I can say that m into, this will be a only. Sorry for the miswriting. So a plus a1 by root 2 minus a2 by root 2 plus m into a plus a1 by root 2 plus 4m into a is equals to 0. Putting a2 to be minus a1, so I will get it to be plus a1. Hence 3m a1 by root 2 plus 6a is equals to 0, and we'll get a1 is equals to 2 root 2a, right? So a1 will come out to be 2 root 2a, and just keep it like this. Well, it will be minus 2 root 2a rather, because it's in the, it will come out to be minus 2 root 2a. So it will be something like this a1 will point in the opposite direction to what we assume, and it will be 2 root 2a in magnitude. Just a minute. Yeah. So I hope you get it. Just reverse the direction of b also in the same way. It will be 2 root 2a in this side, and a2 will be same 2 root 2a, but its direction determined is proper. Now can you divide these all the accelerations into components? You will get it like this direction it will be 2a, and in the horizontal direction for b it will be a. For c, the horizontal acceleration will come out to be 3a, and the vertical acceleration will be 0. For a it will be a itself. Now now we have to consider the virtual work method. Suppose in a infinitesimally small time t, suppose t is very small, so the height by which b will attain at descend, better to say, the height by which b will descend will be delta y, will be half times 2a times t square, which will come out to be at square. So now applying the virtual work method after time t, which is very small. So t is so small that I can assume that velocity of b will be minus at I cap plus 2at minus 2at j cap. Velocity of c can be written as minus 3at I cap, and velocity of a will be at I cap. Now what will be the change in kinetic energy? Delta k will be half into m into 3at whole square plus half into m into 2at whole square plus 80 whole square plus half into 4m into 80 whole square. Now calculating it, you will get it to be 9m80 whole square, right? So this is the change in kinetic energy, and this change in kinetic energy is produced due to the change in gravitational potential energy. Now work done by gravity is equals to displacement of b along the y-axis, displacement of b along the y-axis into mass of b into g, which will come out to be mg into half times 2a into t square, right? You will get it to be mg a t square, and this is equals to delta k, which is 9m a square t square. Cancelling the t square terms, we will get a to be g by 9, and that's the final answer. So the value of n we get it is 9. So hope you got this problem. Well, you can do this problem in another trick or another method, that is assume the tension in the rods to be T1 and T respectively, then try to do it. Or you can also use Lagrangian in this problem. You're free to use whatever method, but just the answer should be coming out to be G by 9, whatever it comes. Okay, so that's it for today. Thank you and have a nice day.